Hey, my name is Max, and today I would like to run a little test for myself and see if I can implement Transformer from scratch following Arena's Colab notebook, where they guide you through implementation, but no implementation is actually done. So I will be discussing how Transformer works quickly during implementation of each layer. However, I will not really delve into the details and theory behind it. So yeah, here, okay, I believe we have to run the setup code again, and then imports should work just fine. Good. So yeah, let's start. And I will skip all of this explanation. It's pretty good and well structured. We will start from here. So, okay, I skipped some code blocks in the beginning. So I guess they just wanted to show, okay, yeah, this. So they load GPT-2 small, and this is what I will try to implement. And yeah, so let's load it. This is not important. This is not important. Quirks of tokenization. Yeah, arithmetics doesn't work, and so on. So yeah, so here's where we get cache from, and yeah, so doesn't really matter that much. Okay, now we can skip all the way through, and yeah, we had to run some cells for this to work. Now we can see shapes of every activation, which is not the same as weight. And here we can see the dimensionality of all of the weights. And yeah, you can define some configs. So dimensionality of our model, this is size of the residual stream. It's quite small. We also have vocabulary of 50,000 tokens, which was obtained by running byte pair encoding tokenization on the dataset prior to this notebook setup. Then we have, well, dimensionality of a hat, which has to be multiplied by 12 in order to get the dimensionality of residual stream, and they have to match up because in the attention you split residual stream into n different heads. In our case it's 12, and each of them should have dimensionality of 64. Well, we make it match basically. Then we have dimensionality of MLP layer. This is where the model reasons about what attention heads had moved, and number of layers is actually number of blocks, number of these blocks, so attention plus MLP. So we'll have 12 layers, and this is our config. And the first implementation is layer norm. I will skip through the explanation, like how to implement it. Will not really look it up. And yeah, so we have layer norm. This is, I think, one of the most boring parts of the transformer, where we have some inputs coming to attention and then to MLP. And for each, we have to implement, we have to normalize input somehow, so gradients will not blow up or not vanish. So first thing that I love to do is simply print shapes. I don't need to print shape of these because, well, it's obvious. The dimensionality of the model is 768. So yeah, we have residual stream where the first dimension is batch. Actually, it's written down here. Second dimension is token position. And the third dimension is dimensionality of a model. Here we assume that token already went through embedding, and now each token is represented by this long vector. And yeah, so what layer norm does, as far as I know, it calculates mean and variance per embedding vector. So we take 768 values in a token, and we calculate mean and variance, and we scale this vector by these amounts times some gamma, and we add bias also. Now, as far as I understand, we do these things to quote unquote give back flexibility level to the model. I'm not really good at this, but intuition behind, as far as I'm concerned, is that we scale these vectors how we like. We let the model decide how it wants to scale it back. So in theory, it can simply restore residual vector, residual stream value if it thinks it's the best way to do it. But we as architects of the model, we encourage some normalization. So how I would go about it is, first of all, we have to find mean and variance per token in our residual stream. So I would do exactly that. And for that, we can use TensorFlow mean function, Torch's mean function. Let's check it up, because I presumed we should have some dimension. Yeah, okay. Along which we want to minimize. Yeah. So we will mean our residual stream along the last dimension. So we will find mean in each vector, and let's also print its shape right away. Okay, so it's 2 by 4. It's all right. However, we have also an option which is called keep dimensionality to true. And what it will do, it will keep the residual stream, it will keep the mean in the same number of dimensions it was before. So if we print it now, it's the same. However, we simply have mean value as vector. Without this option, it will be simply as value here. By the way, it changes, I guess, yeah? Minus 0.01. Oh, well, every time this one is different. Okay, so then it doesn't really matter. And then we can also calculate variance in the same way. Let's also print its shape. Cool. So now they are lined up, and we have mean and variance per token. Now the second thing is that to take square root of variance plus epsilon, and this is done in case variance is 0, which is possible if every value is exactly the same. So if you pass in a vector of zeros, we will get var 0 and so on. And so we add some epsilon, which is defined in our configuration here as 1 to the 10 to the minus fifths. And so this is done in order to not divide by 0, basically. So we can define denom as square root of var plus self-config layer norm epsilon. And if we'll print denom shape, it will be exactly the same as before, so it didn't change anything. And now we can actually start to construct the output. And in this scenario, we will use a term called broadcasting in PyTorch. So now we are trying to perform operation and subtract from residual stream, which is of dimensionality 2 to 4 to 768. We're trying to subtract mean, which is of dimensionality 2 to 4 to 1. And in this case, what PyTorch will do, it will copy means value alongside this dimension 768 times, and we will simply subtract mean from each value here. So in case I will do residual minus mean, and even though their dimensionalities don't really match, you will see that we get back shape in exactly the same way we had initially. So we can actually do this. Yeah, it will be quite a long vector now. And this is this part of the equation done. And now we'll have to multiply by gamma and add beta. So this is also done quite easily. And let me quickly read through. Gamma and beta learnable affine transform parameters. The variance is calculated as biased estimator. Okay. So we've had this weight as simply 768 parameters. I believe this means that we can, yeah, so if we will simply multiply by self w, we should be good. Yeah, and shape of this thing will not change because again we will broadcast the shape, and in this case we are actually multiplying tensor of size 2, 4, 768 by vector just 768. So what this will do, it will create two ghost dimensions and will copy this value alongside. So yeah, and now we can also add beta parameter and we can return. Almost correct. So something is off. Let's see. I believe that it is something funny with variance, because we can, in PyTorch, we can calculate it in different ways, and there is a correction that they use here. Difference between sample size and sample degrees of freedom. This is what I was referring to. So correction is 1 by default, and I believe that this layer norm in GPT-2 expects correction to be 0. Okay, yeah, so that's layer norm. We can now take a look at the solution. Yep, so they just calculated denominator right away, and yeah, looks good to me. So we can move on to the next task, which is embedding. And here this is this part of the transformer. So as an input, we take a sequence of tokens, of course in a batch. So if we print token shape, you will see it's 2 by 4. So it means we have 2 sequences of 4 tokens each. And at the end, we actually expect shape 2 by 4, again, because we map each token, to dimensionality of a model, which in our case is 768. and this is where residual stream starts, basically. So each token is represented by 768 dimensional vector. And yeah, so what we are trying to do here is we have a weight matrix of size 50,000 approximately, don't remember the specific number, by 768, and these all are positional. So when we get position from the tokens value, so for example position 0, it will be position 0 here. So in an ideal world we would do a simple lookup like self e and simple lookup of each token. In this case it will work, so we will pass all the tests right away. However, it's quite unintuitive what is happening under the hood, because what we are doing, we are taking matrix of size 50,000 by 758, and we index it by 2 and 4, and what we get in the end is a nice looking shape actually. So if we were to print the shape of this, you'll see it's actually 2 by 4 by 768. So this is exactly what we are doing. However, you would expect that, wait a second, we should just get one value, yeah, because it will be second token and force value, whatever it is, in residual stream or in embedding vector. It's not the case though, because in PyTorch indexing works in such a way that if you index matrix with, well, let's see, 0, 1, you'll actually get, as you can see, it will be broadcasted because it's in the same brackets. So if I were to do something like this, you see now we're picking actually a single value. So because it's in a single position, Torch understands that it has to broadcast, and it works. So it broadcasts batch dimension in this case. So this is embedding, quite simple to implement, a bit confusing with how PyTorch works, but it's fine. Now we have positional embedding, and in this case we will be implementing learned positional embeddings. So in classical transformer they did funny things with sine and cosine. In order to embed position, sine was a function and cosine was a function of tokens position, and they emitted different waves at different frequencies, and this what allowed transformer in the original paper to distinguish token at each position. In our case, we will simply do learned positional embedding. So again, these two things will be added, I mean positional embedding and regular embedding. So again, we are receiving 3 sequences of 5 tokens, and for each token we want to apply position. And let's see what dimensionality of our weight matrix is. Of course, I forgot self. So it's 32 by 8. Let's see what NCTX is. Oops, I didn't look at it. Yeah. So it's 1024. this is our maximum length. So our model cannot go longer than that. So this is our context window. Okay, now that we know that, we can make sense of this. So here we have 3 sequences of 5 tokens, and in this test example our context length was only 32 and residual stream dimensionality was 8. So in real scenario it will be 1024 by 768. Maybe I will leave it here. And so what we actually want to do is we want to, let me think. Now we don't care what token is in this position, yeah, its value. We care about position itself. So actually we also want to return whatever vector appears to be in this WPOS. However, we want for each sequence its index and not value. Let me think how it can be done. Index select indices. Meh. Yeah. Feeling stupid. Okay. So we get these guys. Nah. Okay, of course we can go like stupid way and simply work it out ourselves, like write the code to get position of each batch, but there should be some elegant way actually. Do we have cumulative sum? I think it can work. So if we will do yeah, it will do sum along the last dimension, and we'll subtract 1. We get position of each token, yeah. So we can do this little trick. I'm not sure if this is how it should be done, but let's do it. Why not? And what's that? It's float. Okay. Okay. So it works. I think there is a much easier solution. So what they did, oh yeah, they actually took sequence length index. It's much easier. I think this one is still okay though, but yeah, definitely over-engineered. I will leave mine, and let's see if it fits later. Now comes fun parts. So position encoding actually wasn't on the diagram, it's here, it should be here, and it will be simply added to residual stream alongside with embed. And this is a element-wise addition actually, and then it will flow into the first layer norm layer. So now we will implement, and they factored it out as a separate task, causal mask. And this is something that is happening in attention head. And this is done in order to prevent model to be able to see next tokens. So this axis, y-axis, is what token wants to see. So it's a query. And this one is key vector. So for example, word step asks how much does how much is your important in this scenario? How much is journey important? And for example, step considers your more important than journey, and actually more than even itself. So it will take information from your token and it will add it to step later. And so this mask is applied in order for token width, for example, not being able to look at 1, because, well, of course, it's the next token. I will simply copy over this information to me, and that's it. So in order for this not to happen, we have to apply this causal mask. And as you can see, each token looks at so it's like a Cartesian product, you can say, with a causal mask. So now, and this is happening inside a single attention head. Let's implement it. I will not again look at the suggestions here. Yeah, so again, I would like to print the shapes, and in this case we get attention scores. We will get to these later in the next exercise. However, here it's a batch size by number of heads. For example, in our case it's 12. So realistic would be 12. Then it's query and key. So this is our sequence length. So for example, 4 and 4. So this is our real size, you can say, that comes to causal mask when all query and key vectors looking at each other and basically providing us attention scores. So what we want to do now is we want to apply causal mask, yeah? So it should be in a form of lower triangle only, preserving the diagonals, because of course token can look at itself. And for example, it cannot look at anything else, so it will simply copy over its information. Johnny, for example, looks at your more, yeah, and so on. So what we want to do is to apply this mask for every head in a batch. So size of a mask should be 4 by 4 in our case, or actually query position by key position. So maybe I will do the mask first, and I believe torch triangular mask. I believe they have method, yeah, called true, which returns upper triangular part. So if we pass an input, it will preserve only upper part. So reverse of what we need. And yeah, it's very easy to fix. So first of all, I will do once, and maybe we can also batch number of heads, I will call it n, and then we can do query position and key position, and this will be our attention scores shape. So now we have all of these dimensionalities in place. We can do torch.once .true, and let's see what mask actually returns. Yeah, that's not bad, and this is exactly inverse of what we want. So now we can simply do this. Or actually it doesn't equal to 1. Let me think. There should be a method to move this diagonal. Oh yeah, so it's called diagonal. And we can simply paste it and maybe read documentation first of what it does. The argument diagonal controls which diagonal to consider. If diagonal 0, all elements on and above are retained. Positive value excludes just as many diagonals above. So in our case, we actually want to include, so we have to exclude. So it's because we'll flip it later. So we should go for positive diagonal. And that's exactly the mask we were looking for. So true is where we will keep the value, and false where we will set it to, I believe, minus infinity. So, and they write it somewhere here, yeah, ignore, and we will set it to minus infinity. So now we can actually apply this mask, and again, it can be done by broadcasting for each sequence in a batch, for each head. However, maybe I will use the thing called inops. And it actually feels quite magical when it works, and when I implemented attention with this, didn't understand the dimensionalities that were involved and how they actually got multiplied between each other. So in our case, we want to repeat this, and we provide it with dimensions, and we say that we want to repeat it like this. So we give it input dimensions, we give it output dimensions, and then we say what output dimensions, additional ones, what they are equal to. And when we will print its shape, we should see unknown character. I believe it's without commas. Okay, so we actually simply broadcasted ourselves right away. This is something Torch would handle just fine. Just wanted to use this repeat in our case. And now we can use the thing called magical Boolean indexing. So now, because we have exact shape as attention scores, we can simply return attention scores mask repeated. Okay, not that magical. Let's see what's happening here. Size of a tensor 15 must match the size of a tensor 5. Okay. I messed up somewhere for sure. Now let's see where. Yeah, okay. So this is not doing what I wanted. Just out of interest. Okay, same. Let's see about Torch Boolean indexing. Because as far as I remember, we can simply generate Boolean mask and apply it like so as an index. But why is it of size 15? What is happening? Okay. We have to preserve dimensions as well. Wait. Okay. Well, it's always me who is not right. So we index this and we actually set it to something, and we set it to ignore, and then we return. So now an entire row to negative infinity. Maybe I do sometimes. Expected actual. Oh, it's actually flipped. I see. Because we created mask like this, we set in all of this to negative infinity. So now we are setting all of these to negative infinity. So this should have been flipped. Okay. For some reason it was more complicated than I expected, but we got it. So now on to the fun part, attention. This is, I wanted to say arguably, but I don't know who would argue with that, the most complicated part of the implementation of transformer, because it involves this. So briefly what's happening is we are going to residual stream, and we want for the model to have ability to move information between token positions and basically be able to see what information other tokens carry. And this cannot be done via MLP layer. This can only be done in attention block, attention layer, however you want to call it. So how it's done roughly is we have residual stream coming in. We split it into 3 different parts, and now I will be talking about single attention head. The following will happen in every attention head. So we split residual stream into 3 parts: keys, query, and values. The splitting is done by multiplying it, by performing a linear operation, which is multiplication by a single weight matrix plus an identity bias. So this is a projection of residual stream, you can say. So projection of all the information transformer currently has. Then we calculate dot products between each key and each query vector. So this projection of information that model has is projected actually in a useful way, because queries will ask questions: who is the most important for me right now? Query vectors. So for example, on this mask, on this diagram, word starts asks, who is the most important for me, your, journey, or starts? And it will say the most important for me is your, well, because it's the first token of a sequence, is quite important in this stage. So this attention mask is formed here by actually just multiplying 2 matrices, as we will see. And then we apply mask in order to restrict model to be causal. We scale it a bit. We apply softmax to get probability distribution for each query. So each query will get probability distribution of, well, values which sum up to 1, well, it will simply see, which model, which token is the most probable for it. And these attention probabilities will actually go and be multiplied with values, and actually not multiplied, but these attention probabilities will be used to average out the values. Again, each value is a vector of token that current token decided to pay attention to. So journey, for example, decided to pay more attention to your and some attention to itself. So we'll copy 55% of your token, and again, it's simply multiplying, the whole value token by 55, and then it will keep itself. It should have been actually 0.45, but it's all right. And it will simply sum up. And we will add this value to current journey token later in the residual stream. So once this is done, we map it back to the dimensionality of residual stream. And well, this is an attention result, which is according to this diagram, as you can see, added element-wise to the information in the residual stream, and then it will flow to MLP layer. So this is the most complicated part. And these are attention patterns which are formed in different heads. So as you can see, most of the tokens, so for example, this head decided I will pay attention to myself. Sometimes, for some reason, it pays attention to token which is like 3 or 4 behind, and that's basically it, like nothing more. Most of them really revolve, some of them highly revolve around the first token, but some, I presume, they will have relative positioning as well. So for example, this head is responsible for looking at relative tokens, like what was a couple of tokens ago. and so on. So these are different patterns, attention patterns that these heads form. And remember, it's only one layer, yeah? So in our model, we will have 12 of these. So 12 by 12, we have 144 attention heads, and they can form that many unique patterns. So this is like heavy shit. Oh yeah, it's even a nicer diagram zoomed in. And we actually can see, yeah, so it's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So it's occasionally selecting a relative token according to some heuristic. Yeah. So this is an attention implementation. I will copy over what we've done for causal mask because we will need it here as well. And let's go over the parameters. So we have our projection to query vectors, which again we will project to 12 heads simultaneously. And we project from. So we will emit dimensionality of heads right now. We project from 764 to 64 because it was dimensionality of our head. And this one was dimensionality of our model. We have 3 of these. We have also 3 biases for these as well. So it's just linear layer. Then we have projection back to the residual stream. And that's basically it. So no more parameters here. Just the way how they interact. So the first thing that we will want to do is we will want to project for 12 heads simultaneously residual stream and our W2 vector, our matrix of projection. And shapes are not looking great. So the resulting shape that we are looking for is actually sequence by batch dimension, by sequence, by attention heads, by residual, by dimensionality of a head actually. So we have 2 sequences of 4 tokens. Each token is mapped to 12 heads. Each head has 64 dimensions for query. So this is the meaning of mapping we are looking for here in this scenario. I believe it also was written down here. So yeah, we want batch, sequence, number of heads, and then head dimension. And shapes which have to produce it actually are not really trivial. They are 2 by 4 by 768 and 12 by 768 by 64. At least according to my findings, Torch does not really work great with broadcasting when shapes are that different. And we will have to help it. So here we will want to insert a ghost dimension because, well, you could say, okay, we want this shape. So we will clearly multiply 4 sequences by this. And this is just another batch dimension. Doesn't work like this. So here we will insert another ghost dimension called 1. And this will allow 12 to go in this place and let these 2 matrices multiply. When this will be done, by the way, I could use in ops in sum for this, and I could simply describe what dimensions are in. I actually I even get the suggestion. So I could do this and it will work. So if we will do shape, I think we will see what we expect to see, which is this. So this is exactly what we are looking for. However, it doesn't say what it did to matrices, and I want to show it and I want to understand it myself. So I will not use anops here. I will use only torch matrices multiplication. And for this, we want to insert ghost dimension here. So let's do this. And in order to insert ghost dimension, we can use method unsqueeze and simply say what dimension to unsqueeze. And when we will do that, we will actually see that now it's in the dimension that will allow torch to broadcast 12 correctly, and it will go in this dimension. Because because how it works, it takes last two dimensions for matrix multiplication. So of course this and this should match, and 12 goes to the just created dimension. If we do without it, I bet 12 and 2 would mismatch. We can also test it and try naive way. Yeah, so broadcasting doesn't really know where to put 12 here, because it tries to put it in this, and well, it doesn't match. Well, everything matches with 1. And if we'll do the same, but with ghost, you see now we fail on test, and well, it's something we expect because we didn't implement attention yet. So when this matrix multiplication completes, we can actually see its shape, and it will not be something we are looking for just yet, because 12 went to another batch dimension. So in order to get our desired dimension, we have to switch these two. It is quite tricky to wrap even my head around it. Like we simply reorder vectors, you can say. Nothing fancy is happening, no operations are involved. We simply do transpose, and we say which two, oh shit, I didn't print shape. And we simply say which 2 dimensions to transpose. And now it's 2, 4, 12, 64, exactly what we were looking for. And this one we can also, let's actually, before doing what I wanted to do, let's do self BQ shape. And this is 12 by 64. You see how it aligns perfectly with last 2 dimensions? Torch will automatically broadcast it. So what we actually can do is we can say plus our bias, and this will be our Q vectors actually. Yep. So this one now is 2 by 4 by 12 by 64. And I will do the same for keys and values right away. I'll just have to be careful with how I do it. But if everything is implemented correctly, now we actually have this projection done in parallel for all the heads by the torch, which is awesome, because now it can optimize it in its own ways and so on. So the next thing I want to work on is attention scores and actually get attention probabilities. So, okay. As I explained earlier, attention heads is dot product between each query and each vector, each query and each key for each head. So we will have to do it along the head dimension, and for this we will want to transpose it back, because now we will have 2 batch dimensions. Yeah, we will have well, batch itself, number of sequences we are processing. This is clear, and this doesn't change anytime soon. But these two, yeah, we want to work in a scope of a single sequence. So token must attend to token in a single sequence. We don't want to mix it up. So it must be, forget what I said about sequences, it must be in each head independently. So this is why we must apply attention along head dimension. So to do it, we have to transpose it back. And again, we can do it by simply calling actually the same transpose. So if we do that, we transposed it back. Now head dimension is actually the batch dimension, you can say. And now this query vector is ready to be multiplied with key. So in case of key, we want to do one more thing, because right now it's the same shape and matrices do not multiply like this. We want to transpose it in a matrix sense. So literally switch rows and columns. There's no fourth dimension, is it? 2, 3. So yeah, now these two will multiply nicely, as you can see. 4 by 64 times 64 by 4. It will produce 4 by 4 matrix, and Torch will broadcast it alongside these two dimensions. So if we now simply do attention score, and this, here what we expect? We expect our two batch dimensions, and then attention score is 4 by 4. So exactly what we've got. This is quite awesome, and we just implemented this part of the diagram. So dot product is actually a matrix multiplication. If you want to take dot product between every vector, it's literally matrix multiplication definition. And yeah, so now we have our attention scores. We have to do boring stuff like scaling it, applying causal mask, and performing softmax. So scale. How it looks like. We divide by square root of dimensionality of keys, which is actually dimensionality of each head. So I will actually do attention props right away, because it will be a lot of operations. And first thing that we will do is we will don't suggest me, I want to do it myself. We will divide by square root of dimensionality of a head, and if we were to print it, we will see that dimensionality didn't change, but it also failed. Why you failed? Isn't it called D head? It is. Tensor, not an int. Okay. So it can broadcast. Okay, fine. So meh. Holy moly. What is this? Okay. Well, I don't know semantics of torch really well, so I fail sometimes at such tasks. So it assumed it's a size and populated with zeros. Fine. So now I will actually turn on my lights. Because it's starting to get quite dark, unfortunately. Okay, so we have our scaled attention. Next thing that we want to do according to this perfect formula, where is it? Is we want to apply mask. So attention will not, so tokens will not see each other. This is done like so, because we've already implemented this. As you remember, this function, it accepts exactly batch, number of heads, query position, key position. Dimensionality will already possess. So this one, an easy one. And last thing that we want to do is apply softmax. And this thing basically makes everything sum up to 1, which is called in a fancy manner probability distribution. So whatever values we got from attention scores, they will now sum up to 1. And as you've seen from this picture, if there is only one value, of course, it is 1, and so on. So, of course, there is a function for that in PyTorch. And the last thing that we have to be careful about is along which dimension we perform softmax. Because, well, there are 4 dimensions. Of course, the first 2 are batches, but then we have query dimension, which is like asking, hey guys, who I want to pay attention to. And then we have key dimensions per token, which are screaming me, me, me. So we want these values, so key values, to be summed up to 1. And this is our last dimension. So if I do -1, we get real attention probabilities now. And I think I can actually even print them because there are not that many. And yeah, as you can see, we're getting them. So the first token is always 1. And then they all sum up to 1. Of course, these are most likely randomly initialized. So attention doesn't really make sense. And it's like random noise for now. But still. So we have attention probabilities here, and this is this part of diagram done. Now the last part is actually like one of the most complicated parts. Is specifically for me was actually figuring out torch quirks, how to get this working, like the linear projection, which seems very easy. This one was easy. This one was easy too. And this one was quite complicated, especially for me as well. At least as far as I remember, maybe I'm lying. So let's see. Actually, I didn't write our dimensionalities here. It would be useful. It's actually the same. So what we want to achieve, we have this matrix as input. We don't want to multiply it just yet. I think we will, and we will. But what we're actually doing is we are now kind of replacing, at least inside of this attention head, because later it will be added to residual stream and we will not replace the token value really, we will add. However, in this case, we're actually replacing current token values, so these 64 values which token has, with averaged sum of new value vectors. And these value vectors, they are summed up. It's called average sum because we use attention probabilities to figure out how to replace current token and what it paid attention to most, and what it paid attention to most and how do we replace it. So this is our props, and this is our value vector. So value vector got actually unchanged. And what we expect from this operation is, of course, batch size. Then we want sequence, number of heads, and dimensionality of each head. Let's check the diagram if it actually matches. So we want batch, we want sequence, so it's like number of tokens in each sequence, we want number of heads, and we want oh sorry, I was looking for on the wrong one, but it's actually the same, and we want dimensionality of a head. So this is input and output shapes, and of course we'll multiply it. Maybe now I will remove it. And yeah, so it's actually quite easy. So from here we can say that, okay, now we want to perform operation for each head again, I believe. Let's read the annotation here because I actually forgot a bit. We apply a final, not this. For each destination position, we take a weighted average of value vectors from each source position in accordance with how much attention destination pays to source. In other words, we multiply attention props by values along SK dimensions, so the last one. All right. We multiply attention props by values along SK dimension. Weighted average of values, yeah. So actually, what we are doing completely forgot that one. Yeah, so we'll figure out it from the start. Let me think. So here we have attention props. These are actually weights for each attention head, and for each token sequence how much it refers to another sequence. And this is value matrix, yeah, value vectors. We have two sequences of 4 tokens, and in each attention head we have 64 of these. So the first thing that I would want to do is to switch these dimensions, and in this way we will work alongside the head dimension and not sequence dimension. And so this will stay batched and will work like per sequence in each head. So, and then these shapes actually match, yeah? So if we will multiply this, we will get 212, 464. Of course, we will simply redo it and we will get this. So yeah, it feels like we have to transpose value vector and then apply attention mask. And let's see if this multiplication operation actually makes sense in terms of semantics, what it will do. Yeah, so for each sequence in each head, we will, and this is now 4 by 4, because it's now in a single head, 4 by 64. These are our value vectors, yeah, and if I were to write it out, yeah. So we take the first query, we say, oh, I actually paid attention to myself fully, yeah. We take the whole vector, 64. Then we take the second one, and we take average sum of two value vectors according to the key scores. So I like it. I feel like semantics actually match. And I feel like that's what we will do. So we will do attention probes. And then we will do value, but we will transpose it again. We will switch these two dimensions. And this should give us for each head we now have a weighted average. Now, in order for Z to match our dimensions, we have to transpose it again. And since we will not use it anywhere else, we can simply transpose it right over here. And last thing that is left to do is, actually I don't want to print these anymore. Last thing that is left to do is to apply our output matrix. Meh. Okay, so again, the same trick that we used in the beginning, but now it will be the other way around, it seems like. So, of course, we want to multiply each token. So we'll multiply this and for each head. Yeah, let me see where we sum up. Yeah, we map linearly and then we sum up and then we add bias. Okay, so in this way we want to do it per head. Sorry, I scrolled way too far. In this case we will want to do it for each head. Yeah, so we will do what we will do. Head is a batch dimension. It's actually non-trivial for me again for some reason. So let's see. We have Z and our output vector. Where is it? Yeah, so let's go here again. Yeah, so, and we simply map. Yeah, so it's the same shape but different dimensionality. So we want to map this 1264 times 1264 768 and get to 412 768. That's what we want to get. The same shape, but with different dimensionality in the end. Yeah, and then we will sum up all of this alongside head dimension and have 2 by 4 by 768 at bias. We are happy. So the last matrix multiplication left. How do I figure out how Torch broadcasts? If I will do that, well, this one will not match. What actually am I trying to achieve here? So on this side, of course, I want to multiply 64 by 768. Yeah. On this side, it almost feels like I want to do actually this, because I want to be along head dimension, and now I will have 4 tokens in each head, and for each of them I will have dimensionality set up, and this way I can actually do this and it should work. So this transpose is actually false, and we have dimensionality here of 2 by 12 by 4 by 64, if I'm not mistaken. Let's see. Yep. And actually, I think even without adding this ghost dimension, it should work nicely. So if I were to do, yeah, it almost attention out. Don't suggest me anything. Matmul Z with self. This time I will not forget it. Let's see. Yeah. So this one is good. I presume that we have bias in a shape of 12 by 764. So let's see. Oh, actually, I think we'll even have just 764. Yeah, because it said it in the end. I forgot. Okay, so now, once we have that, actually, it's now 12 by 4. Yeah. So this one explains this. This is quite clear. This is not quite clear, but it's all right. This one explains this. This one explains this. And now when we have attention out, we have attention summed alongside head dimension. So in our case, it will be attention out sum by dimension 1, because this is our head dimension. And now we actually have to see that this shape is exactly 2 by 4 by 768. And of course I forgot to do dot shape. So this is now shape of our residual stream. So if we were to go back here, we are now here. And the last thing that is left to do is actually just return bias. So actually, I think I will just do that. Nah, okay, it's all right. Correct. So again, even like deriving it again wasn't easy. Every time I'm like, how this shape are gonna match and what am I doing and am I doing it correctly? But every time seems to work out. So yeah, here transpose was actually false. We actually wanted this to be batch head dimension, because inside of attention we work on head level and sequences are per head, and when we want to go back, well, this here we didn't even have to transpose because we sum over this head dimension. So the hardest part done. Now we have MLP, and in case of transformer, it's implemented like as it's the same fan in, fan out, but at the center it like grows actually 4x. Reasons behind this are fun, and Neil Nanda goes very deeply explaining them in his videos, but there is no good reason behind it. Basically everyone does the same. So what we will need to do now is we will want to see what shapes we are working with. So we have input coming in, and I presume it will be 2 by 4 by 768, and we have the first MLP layer. Well, this one is a no-brainer. We can simply multiply it, and it works. I will return right away. Now this dimension is 2 by 4 by 3000 whatever we had, and we actually have to add bias, which is just dimensionality of MLP. And at this state our activations are at their highest point, so they take up like 3000 values. And now we want to scale back to the size of residual stream. We presume the model thought enough already, and this is done by another matrix multiplication and by adding another bias. So I forgot something. What have I forgotten? Let's see. Looks all right to me. I don't know. What's wrong? Multiply this, multiply that. We do not put any normalizations yet. Okay, let's print its shape. Should be 2 by 4 by 3000 something. Okay, this one is clear. All right. So I will do okay. Then oh, that's what I have forgotten. This time autocomplete actually helped me, but of course we had to add non-linearity, because who doesn't like non-linearity. And I think in this notebook we have GLNU or something. Yeah, so this is a function from transformer lens. All right. So we will use that. And we will use it here. So on the wider level, we use it. We do activations, and yeah, that's it. So it's a single line actually. It's not very pretty, but it's all right. And solution was open for some reason. That's it. Like all internal parts of the transformer done. And now everything that is left to do is only to implement its block and then the whole transformer itself. This should take like exponentially less than it took me to implement even attention only. But let's see. So transformer block is actually this. And how it works, the input to each layer inside a block, of which are two, attention and MLP, we apply layer normalization. So when we have residual stream, we do this. And now we can actually not care about dimensionalities at all, because all of these layers already work with residual streams. After, do not suggest me. After residual stream, we have attention. Then, as you can see here, outputs of attention are actually added back to residual stream. So what we want to do is actually do this. Don't suggest me. It's so easy that like it, after every character tries to suggest me something. So okay, it's so easy, I will just accept it. So we add it back to residual stream, then this residual stream actually goes to layer normalization too, and then it goes to MLP, and we add MLP to residual stream, and this is like, I would call it reset final, and it should just work. Of course, human typing is not perfect. All right, and this is transformer block implemented. Again, when you don't have to deal with dimensions, it's quite easy. And now we have to unembed. So this is the last step before getting logits. We have to unembed. So going back from dimensionality of residual stream to dimensionality of vocabulary. So when residual stream is coming in, again, we have these dimensions 2 by 4 by 768. I bet you already got a bit tired of me repeating it. And dimensionality of our unembed matrix is actually 768 by the cap. So we can actually just multiply right away. Normalized residual stream by self WU. Well, here what will we get? 2 by 4 because they were broadcasted by this 50,000 something. And our bias is already 50,000 something. So we can simply edit and hope that the torch is good enough to broadcast this one as well. Well, apparently it is. So it was quite easy as well. Now we have demo transformer where we have to implement forward pass for the whole transformer decoder block. Yeah, I don't want to look at it. So we get tokens. What do we do with tokens first? We embed them. Embed post. And we... No, wait. I didn't finish. And we encode them positionally. Then residual stream is actually these two together, added element-wise. And dimensionality is already $768. Now, after this, after we embed it, it's always just blocks and nothing else. Do not suggest me. Do not suggest me. Do not suggest me. Doesn't listen. Okay. So, I cannot. Okay, this one I didn't write yet, but this one is very easy. So, we perform a block operation, which is, well, head plus MLP. Back to residual. Here we can assign instead of adding it up, because transformer block already adds it up for us. So a simple assignment will work. And after all blocks are done, I think we have to perform linear normalization one last time before unembedding. I actually don't remember this good. I believe so. Will be a little bit of a bet, yeah. So once all blocks are done, I can say ln final post. Okay, he got me. Then we unembed the results of this post, and we actually get logits. Our magical logits. Let's see if this is correct. Ding, ding, ding. Looks like it is. So we can now, using our demo transformer, load in weights of an original GPT-2 transformer and get some log props. Run the thing. So here it is. So now it's generating tokens, and I'm actually not sure what kind of sampling algorithm is used under the hood. Maybe it's... I think it's, if it's from official library, it should be sampling with top P, I believe, or top K. So let's wait for the result. Yep, so this was written by human. Mitigating the risk of extinction from AI should be a global priority alongside the societal scale of risks such as climate change. Yep, the spread of infectious diseases. You know it. I think it was trained in 2018 or 2019, so it didn't get to see COVID yet. Quite good vision. And the spread of infection diseases. Again, very insistent on this. Maybe it knew something. Research was published. Well, then it's just gibberish, yeah. So once the sentence is over, even before the sentence is over, it's already like doing some weird stuff. But weights are loaded in. It works. Quite happy with the result. Maybe it could have been a bit faster on attention bit, but yeah, actually when I opened their solution, I was like laughing because I was trying to figure it all out in PyTorch, and then they're just we will pass this and let magical in sum. It's really magical. Like matrix multiplication is just like one of the cases of in sum, and it does like crazy shit. But I don't understand what is happening under the hood when I define my operations like this. So it's very useful, but unless you know what you are doing. So yeah, I was quite disappointed to see this, and I was quite happy to work out this. So yeah, I didn't think it was useful for you. It was quite useful for me though, but thank you.